Hello students, I welcome you all in our lecture 16. So, in the today's lecture, we are going to study Henderson-Hasselbalch equation of buffer solution. Hello students, in the previous lecture, we have seen what is a buffer solution. The solution which maintains the pH or which resists the change in the pH is known as a buffer solution. These buffer solutions are of two types, that is acidic buffer plus basic buffer. Okay, so this maintains the pH less than 7. Okay, this maintains the pH greater than 7. Okay, this is the basic. In the previous lecture, we have seen how to prepare an acidic buffer solution and the basic buffer solution. So acidic buffer solution was made by mixing an aqueous solution of weak acid with the solution of its salt with the strong base. That means it is prepared by mixing the solution of weak acid plus its salt with strong base. Okay. Similarly, for the basic buffer is prepared by mixing an aqueous solution of weak base with the solution of its salt with strong acid. That means it is prepared by mixing weak base with its salt of strong acid. So here we will take the examples. So if we consider any acid which gives H plus ion and A is an anion, okay, plus its salt with the strong base. So here, for example, we will take a strong base as a Na and this anion is common. So this is made by mixing weak acid with its salt of strong base. Similarly for this, if this is prepared as BOH, which is a weak base, plus its salt of strong acid, that means BCl. Okay, for example, we consider that HCl is a strong acid, that's why we will take this common. Okay, so now in the today's lecture we are going to study the Henderson-Hasselbalch equation. Henderson-Hasselbalch equation for buffer solution. So in this equation, consider an acidic buffer solution. So in the acidic buffer solution, we know that there is a presence of Ha plus NaA. Okay, this is a weak acid. This is its salt with the strong base. We know that Ha is weak acid. Weak acids are weak electrolyte which does not get completely dissociated. So it forms an equilibrium with H plus plus A minus. Similarly, in our solution, there is NaA, which is a salt, and we know that salts are the strong electrolyte which gets completely dissociated. Na plus plus A minus. Okay. Now, in the previous lecture, we have studied the common ion effect. So, the common ion effect tells us that the dissociation of any substance in the presence of the solution containing the common ion gets suppressed due to the presence of that common ion. So, the dissociation of Ha gets suppressed due to the presence of A minus already in the solution. As we know, Na is a salt which gets completely dissociated. So, in the solution there is already presence of A minus, and due to that what happens, the equilibrium shifts to the left. The equilibrium shifts to left. Why? Due to the common ion effect. Okay. So now applying the law of chemical equilibrium, so according to the law, Ka is equal to, for the equilibrium, concentration of H plus into concentration of A minus upon concentration of Ha. Okay. But we know that concentration of A minus in the solution is equal to the concentration of NaA. Why? Because Na is a salt and it gets completely dissociated. So whatever is the concentration of A minus is equal to the concentration of NaA. And we know that NaA is a salt. Okay. Now putting that in the equation, Ka is equal to concentration of H plus into concentration of, instead of writing A minus, we are going to write concentration of salt upon concentration of Ha. Okay. So now instead of writing the concentration of Ha, we can write concentration of Ha is equal to concentration of acid. Okay. Now putting that in the above equation, Ka is equal to concentration of H plus into concentration of salt upon concentration of acid. In the next step, what we will do? We will shift these all terms to left hand side and there will be only concentration of H plus. So concentration of H plus is equal to, so acid gets multiplied to Ka concentration of acid upon concentration of salt. Okay. Now taking negative logarithm to both the sides. Okay, so minus log of H plus ion is equal to minus log into curly bracket that term Ka acid concentration upon salt concentration. Okay, so now we know that negative logarithm of H plus ion is nothing but it is a pH, which is equal to minus log of Ka in minus log of concentration of acid upon concentration of salt. Okay, so pH is equal to, we know that minus logarithm of Ka is pKa. This we have studied in the previous lectures. Now plus, so here we have taken the plus log of concentration of salt upon concentration of acid. We have taken the reciprocal, that's why this minus has become plus. So the final equation is pH is equal to pKa plus log concentration of salt upon concentration of acid. Okay. Now this is known as Henderson-Hasselbalch equation of acidic buffer. Okay. So now what is the need of Henderson-Hasselbalch equation? So now Henderson-Hasselbalch equation is used to calculate the pH of the acidic buffer solution. By using this equation, we can calculate the pH of acidic buffer solution. Now, for the basic buffer, solution, Henderson-Hasselbalch equation will be, so there we will find the pOH of the basic buffer solution. Instead of pKa, there will be pKb plus log of concentration of salt upon concentration of base. It is this equation we can compare with the equation of acidic buffer solution. Okay, so this is the Henderson-Hasselbalch equation for basic buffer solution. Okay. So this was all about the lecture. In the today's lecture, we have studied or we have derived the Henderson-Hasselbalch equation. Okay. Now we will stop here. Thank you.